No, I was playing handball. All right. So today is the last day that we're learning something. So hope you guys are all excited for the last lesson. Kind of sad. Why would it be sad? Why? What's going on with 156? Is it like, do you need like another requirement or something? Hmm. Yeah, I don't know. Should be fine. I mean, it's what do you need for one? I don't even think you need any requirements for 156. But yeah, I wouldn't know what's going on. I'm sure they'll fix it because like if they don't fix it, then everyone's gonna riot. So I wouldn't be worried. All right, so today is about Taylor series. That's our last topic is Taylor series. So um, let's jump right into it. So Taylor series is actually very similar to a previous topic. You guys remember power series? That was, I think, 2 topics ago we learned about power series. So this is related to that. All right, so let's see. Um, here's the motivation. So if you guys remember what we did in power series, we well, specifically the topic that we use power series to represent a function. So what we did was anytime we had a function, we had to get it in the form 1 over 1 minus something. And then once we got it in that form, then we could write it as a power series, right? So that was what we learned to do before. Now, that's fine and all, but like that method is actually like very, very specific. In other words, like it has very limited uses, right? Because there's a lot of functions and a lot of them can't be written in that form. So it's only when you're able to write it in that form is when we're able to write it as a power series. But what happens if you're not able to write it in that form? Right? So this is where the Taylor series comes in. Okay, so going back to the notation for power series, this is the notation right here. So it was summation of C of n times x minus a to the nth power, right? So that's a power series. Do you guys remember what C of n and a were called? Yeah, so C of n is the number in front of each term. So we call that the coefficients. And then A is basically the center of your series, right? Which for all questions should be given to you, right? All questions should give you the center. Like it should specify the center. So that's a power series. What we're gonna do is we're gonna give you a method to figure out what the coefficient is, all right? So we never really explain like how to find the coefficients. So in Taylor series, there is a formula for the coefficients. So if you look over here, it says, now consider letting the coefficients be the following. So C of n is equal to f to the n of a over n factorial. So what does this mean? Do you guys remember the notation for derivative? So things like f prime, f double prime, f triple prime, and all that stuff. Do you guys remember that? Okay, so let me just write it out for those of you who haven't seen it before. So if I have just a function f of x, you can sort of think of that as like the 0th derivative. And then you have f prime of x, which is the first derivative. And then you can also have f double prime, which is the second derivative. And then as we go on, it's kind of tedious to write a lot of apostrophe. So for the third derivative, we usually use this notation, f to the third of x. So that's the third derivative. And then this is the fourth derivative, okay? So yeah, this is f to the 0 of x. This first derivative, you can also write it like this. And then second derivative can also be written like this, okay? So this is just derivative notation. And then as you go further and further down, you can generalize it to like f of the nth derivative of x. All right, so now switching back to the PowerPoint. So the coefficients is basically just the derivative at the particular center over n factorial, okay? So that's gonna be the new coefficient. So once you replace the coefficient with that formula, you're gonna get the following. So you're gonna get summation of f to the n of a over n factorial times x minus a to the nth power. And this is basically the formula for a Taylor series, okay? So you'll need to know this, write it down in your notes. And then the next line is just what happens when you expand the Taylor series. So if you write down every term, that's what it looks like. All right, so I'll give you guys a moment to jot that down. And then we'll talk about like what it represents. This PowerPoint is already uploaded, so don't worry if you don't get it. Anyways, let's talk about what this series represents now. So it's kind of similar to a power series, like we said. Do you guys remember how a power series represents a function? So from power series, we said that if you have a function, you can write it as a power series. And the power series basically is a polynomial that represents the particular function, right? And then as you add more terms, like as you list out more terms in the power series, then the polynomial better represents the actual function, right? So that's the main idea. And Taylor series is actually the same idea here. So however, it's more specific. So the way a Taylor series works is you're trying to match the ordered derivatives with the actual function. So what I mean is that let's say you have a function. Let me actually write it out here. So let's say I have a function f of x. And then let's say I have the function equal to a Taylor series. Like this. Okay, so this right here is the Taylor series for f of x. So let's say the center is A. So center is x equals A. what's going to happen is you're going to have f of a is equal to f of a here, and you're going to have f prime of a is equal to f prime of a for the Taylor series. And then you're going to have f double prime of a is equal to f double prime of a here. So basically, you're just trying to match all the derivatives from the left-hand side to the right-hand side. Okay, so that's how a Taylor series works. Yeah, okay. And then in the Taylor series, we have the center still, right? So the center is A. There is one case where if you let the center be equal to 0, so if you go to your Taylor series, which we have on top here, if you let A equal to 0, then you're going to get the following. You're going to get this blue part on the bottom. So notice I just plugged in 0 for A, which gives you this. And then when you do that, the Taylor series has a special name. It's called a Maclaurin series. So yeah, all these names are named after mathematicians. So yeah, but a Maclaurin series is basically a Taylor series with the center equal to 0, okay? Now, I will say that when we're gonna do problems on Taylor series, I would say about like half of them will have the center be specified to 0. So it's really not that uncommon to have a Maclaurin series problem. It was pretty useful. Okay. All right. Okay, so here is the first example we will look at. So here I have the function e to the x power, which you guys should know very well. And then on the right side of the equation, we have the Taylor series for this function e to the x. So the Taylor series for e to the x happens to be this summation right here. So it's summation of x to the n over n factorial, okay? Don't worry about how we know that yet, just accept the fact that it is for now. And we'll do some observations. So let me pull up a graphing tool. So we have e to the x, which I will graph right here. So there's e to the x. Okay, so this Taylor series is centered at 0. So we're gonna zoom in on the middle portion of our graph near the origin. So the main idea is that we want to approximate this e to the x function with a polynomial, but how do we do that? So the first thing we want to do is, well, if you're gonna approximate a polynomial for this graph at 0, then the least you could do is give it the same y value when x is 0, right? Which means you're going to have y equals, what's the y value here? It's 1, right? And then you're like, well, okay, that's fine, but that's nowhere close to e to the x. In fact, they look totally different. So then what you do is you say, okay, well, since giving it the same y value is not enough, let's give it the same first derivative. So the first derivative evaluated at x equals 0 happens to be 1 times x. So it's plus 1x. So now we have this. So now we have a polynomial to the first power that we're trying to approximate e to the x with, which I don't know, I guess you could say is a little better because like it has the same y value and it has the same derivative, but it's still not that good, right? So then we say, well, okay, let's make them have the same second derivative as well. And then according to the Taylor series, it's x squared over 2 factorial. So that's plus x squared divided by 2 factorial. So now we have this. So can you guys see what's happening? So as I'm adding more and more terms from the Taylor series, into the equation. The blue graph better approximates the red graph. So basically, it's just like what we did with the power series. All right, so I know that was a lot of information. Anyone want to ask any questions or comments? All right, looks like we're good. All right, so now let's move on to figuring out how can we actually find the Taylor series for a particular function. So over here, we just gave you that e to the x is this Taylor series. But then again, like, how do we know? So let's do an example. Let's go over here. So example 1 says, find a Taylor series for this function about x equals -1. Okay, let me just write this down. Okay, I will paste the Taylor series formula and put on the side here. So here's the question, and then we're trying to use this formula on the right here. Okay. So let's think about what we are given. So we're given the function, and we're given the center, right? The center is -1. We can plug in the center right away. So let's do that first. So this is going to be f of x is equal to summation n equals 0 to infinity. This is f nth derivative. The center is -1, so that goes here. And then we have n factorial, and then x minus -1, so that's +1 to the nth power. Okay, so that's what our Taylor series is going to look like. Okay, so now let's think about what we need to fill in this series notation. So remember, a Taylor series is a power series, so it's supposed to be a function of x. So x can just stay in x. We don't need to fill that in. And we also don't need to touch, right? Because that's just the index of the summation, so we don't need to do anything with that. The only thing we need to figure out here is this part right here. So this f to the nth derivative of -1. That's the only part we need to figure out. So we need to find what this is. So how can we do that? So a warning, finding that part is actually quite an involved process. So I actually went ahead and did ahead of time. It's on the next slide of the PowerPoint, so I'll just copy and paste it here to let you guys see. Okay, So the first thing we're going to do is actually just take the derivative of the function a few times. So here I have the first three derivatives of the function. I don't expect you guys to take this, like take notes for this because we're going to be going like quite fast. Well, not fast, but like there's a lot of stuff. So I would say just pay attention for now, okay? So the derivative of 1 over x squared is negative 2x to the third. And then the second derivative is that. And then third derivative is that. And then the goal here is to list out enough derivatives so I can see the general form of the pattern. So I've actually written down the pattern down here. So f to the n of x is actually negative 1 to the nth power times n plus 1 factorial over x to the n plus 2. Do you guys see why that's a pattern? Let me know which part you guys want me to explain here. Okay, the whole thing. So the first part is just the function itself. So this is just the regular function. When you take the derivative, you're going to get this part right here. So notice how the numerator just went up by 1. Sorry, the numerator got multiplied by 2, right? And the denominator just went up by 1 degree. And then when you take the derivative again, you get this. So the numerator got multiplied by 3, and then the denominator degree went up by 1. And if you take the derivative again, then the numerator got multiplied by 4, and then the denominator went up by another degree again. So basically what's going on is like the numerator is being multiplied by the next integer, right? So first is being multiplied by 2. So going from here to here, it's being multiplied by 2. Going from here to here, it got multiplied by 3. Going from here to here is being multiplied by 4. And then the denominator is basically just going up by a degree of 1. So what's happening is the numerator, eventually the numerator is going to be this. It's going to be 1 times 2 times 3 times 4 times 5 and so on. That's what's happening to the numerator. So that's why we have this n plus 1 factorial over here. Because notice how when n is 3, you get 4 times 3 times 2 times 1, right? And then when n is 2, you're going to get 3 times 2 times 1. So the pattern is n plus 1 factorial for the numerator. Is that okay? So that explains the n plus 1 factorial part. And then we want to see the pattern for the denominator. So notice how when n is 3, we have x to the 5th power. When n is 2, we have x to the 4th power. And then when n is 1, we have x to the 3rd power. So the exponent is basically 2 more than the pattern, or sorry, 2 more than n. So that's why the denominator is x to the n plus 2. And then because they're alternating signs, then we just have this negative 1 to the n here. So hope that clears it up a little bit. All right, let me just paste it back just so we don't have all this notation. Okay, any other questions regarding how we found the pattern for the derivative? Okay, so once we find a derivative, that means what we have is, we have this, right? We have fn of x, but that's not really what we want, right? We want to find f of n of -1. So what we need to do is we need to just plug in -1 into what we just found. So let me just go ahead and do that. Okay, so when I plug in -1 for x, I get this. So this is where the x was. I plugged in -1. And then from there, I'm going to simplify. So this is basically, let me show the simplification process. So I have -1 times n plus 1 factorial. And then I have -1 to the n plus 2. So that's n, and then -1 squared, right? So what happens is these two cancel out, and then -1 squared is just +1. So that just goes away. And then n plus 1 is left. So that's why this simplifies to just this, okay? All right, so yeah, we've done it. So we found f to the n of -1, which is n plus 1 factorial. That means we can write our answer for our Taylor series. So our Taylor series for f of x is going to be, let me just write everything else. So it's n factorial, x plus 1 to the n power. And then f to the n of -1 is n plus 1 factorial. Right, so that's our Taylor series. I think we could simplify this a little more, right? So n plus 1 factorial over n factorial. Do you guys remember what that is? Yeah, so that's just n plus 1. Okay, so that's our answer. Wait, I'm missing something. I'm missing the summation sign, my bad. Where did the n factorial come from? That's part of the Taylor series formula. So it's the denominator here. So this is the part that, this is one part of the Taylor series formula. The only thing we were trying to find on this work here, we were just trying to find this part. So once we found it, then we just plugged it in. The n factorial is just part of the formula. Are you asking like, why is it part of the formula? Is that what you want to know? About, oh, that's the center of our series. So this is like, this is the -1 is basically like your A. So -1 gets plugged into A. Did I not give you permission to record? Oh, did you ask? Did I miss you? Oh, okay. All right. Yeah, Taylor series is, I would say, is probably the hardest topic in Calc 2. This is like the final boss. So Yeah, I wouldn't be surprised if you don't get this the first time. You have to remember this formula. I mean, the way we're learning right now, you don't need to remember anything. But yeah, I guess like for like normally, yeah, you would need to know that formula because we will use it. Yeah, I would recommend you to know it. Anyways, go back to the PowerPoint. Yeah, so just a recap of the question we just did. So we had to find a Taylor series for 1 over x squared about the center of -1. So what we did was we found the derivatives, and then here are the derivatives. We found a pattern for the derivatives. So as we find more and more derivatives, we try to figure out what's the pattern that's going on here. And then we try to find the general form of the derivative, which happened to be what's on the bottom there. Yeah, and then we evaluated the derivative at -1, which gives you this middle column, which simplifies to n+1 factorial. So that part goes into the numerator part of our Taylor series formula, okay? And then that's your Taylor series. All right. Let me go back to, let me do an illustration as to what's going on in a Taylor series a little bit more clearly, because I think it'll help. Okay, let's look at this example from earlier today. So the one for e to the x. So f of x here is just e to the x, right? And then f prime of x in this particular question is just e to the x again. And then f to the second derivative is e to the x. Well, I mean, that's just a special case for this one, but let's just keep writing out. So the third derivative of x is e to the x. And then if we evaluate this particular function at the center to be, let's say the center is 0, then we're going to get e to the 0 power is 1. And then the first derivative at 0 is also 1. Then the second derivative here is also 1. And then the third derivative is 3 is also 1. So the point of a Taylor series is to match the derivative values for the left and right hand side. So if I take the right hand side now, which is this polynomial, so if I write the 0 degree polynomial, so 0th degree, that is just the number 1. If I write the first degree, that's the x plus, well, I'll write it the other way. So it's 1 plus x. And the second degree is going to be x squared over 2 factorial plus x plus 1. And then the third degree, which is x cubed. I started writing it the other way again. It's fine, doesn't matter. Plus x squared over 2 factorial plus x plus 1. So let's see what happens if we evaluate all these polynomials when we take the derivative and then evaluate it at the center. So for the first polynomial, which is the 0 degree, when we evaluate it at 0, we're going to get just 1, right? For the next one, when we take the derivative, what do we get? So what's the derivative of x plus 1? Yeah, it's just 1. And then when you evaluate the derivative when x is equal to 0, you're going to get 1 again, right? So let me just center for this question was 0. And then for the next polynomial, so this is the next polynomial. For this one, we're going to have to take the derivative twice. So when you take the derivative of this polynomial twice, what do you get? Let me just make sure of that. So it's x squared over 2 factorial plus x plus 1. So when you take the derivative once, it becomes x, oh, it just becomes x plus 1, right? And then when you take the derivative again, then you're going to get 1. And then when you evaluate it at 0, it's still 1. Yeah. So then for the next polynomial, for this one, we need to take the derivative 3 times and then evaluate it at 0. So then that's going to be 1. So this is basically what a Taylor polynomial is doing. It's matching the derivatives on the right-hand side with the derivatives on the left-hand side. So notice how this value matches with this value, and then the first derivative at 0 matches the first derivative of this function when it's equal to 0. Here is a second derivative, here's a second derivative. So that means I have to take the second derivative of this function and then evaluate at 0, which turned out to be 1, which matches. And then here is the third derivative. So we take the third derivative here and then evaluate at 0. So that happens to be 1. So hopefully you guys see the picture. It's matching the derivatives. Each order derivative is being matched. So that's the main idea of a Taylor series. All right, so let me just erase this. So for example, if I gave you, say, n equals 3, then that means we're going to have this function. And then because n is 3, that means we're going to have just like to the third power, right? So we're going to have this. This is not the whole Taylor series, this is just part of it. You guys can verify that if I take the third derivative of both sides of the equation and then evaluate it at the center, it will have the same value. So if I take the third derivative of this function and the third derivative of this function and evaluate it at 0, they should be the same. And this will work no matter what n value I specify. So I can even say like n equals 4. So then you can add the next one, 4 factorial. They will have the same fourth derivative, and they will, yeah, they'll have the same fourth derivative, and when you evaluate them at 0. So that's the main idea. All right, I think that's good enough. Let me go on to the next thing I wanted to talk about. Okay, so what's the relationship between a power series, a Taylor series, and a Maclaurin series? So a power series is like the broadest term. It's the most general one, which is summation of C of n of x minus a to the nth power. So that's a power series. When you specify that the coefficient is f to the n of a over n factorial, then all of a sudden your power series is now called a Taylor series, okay? So a Taylor series is just basically a special kind of power series. And then if you let the center be equal to 0, then you have a Maclaurin series. So a Maclaurin series is a Taylor series, and a Taylor series is a power series, okay? But not the other way around. It's kind of like the square and rectangle thing. All right. So next we'll look at some questions that are more representative of like what I'll test you on for power series. I mean, for Taylor series. So you guys can see what what I expect you to know going into the exam. Actually, wait, no, never mind. I still have some other things to say. So a Taylor series has an infinite amount of terms, right? Because if you look at the summation, let me go back. So a Taylor series, the index is at 0 and the ending index is infinity, which means it's an infinite series. So there's an infinite amount of terms in the polynomial, but you don't actually have to write all of them out. You can actually just write out like some of the terms, right? So let me go back to the E of X example again. So here, so there's this thing called the nth degree Taylor polynomial of f of x. So going back to paint. So if I ask you guys to say, for this particular example, write out the I don't know, second degree Taylor polynomial, what would that be? So the way it's written right now, it's an infinite series, right? Because the degree is infinite. But what if I told you just write out the second degree? How would you do that? Can you guys see? X squared over 2 factorial. Yes, but like it has more terms. So you have to write out everything under it as well. So that it will also be including the x and the 1. So that will be the second degree Taylor polynomial, okay? The notation we give to this is t subscript 2 of x, okay? T sub 2 of x. So if I asked you to write down t sub 3 of x, you guys think you could do it now? What would t sub 3 of x be? Yeah, you could write it like that. Yeah, either one of those is fine. But I'll just write out the whole thing. So it's x to the third over 3 factorial plus x squared over 2 factorial plus x to the first. I mean, technically you could write it like this as well. This is the same thing, plus x to the 0 over 0 factorial. No. This is not what I'm going to test you on. Coming later, but this is just some more notes about Taylor series. All right, let's go back to the PowerPoint. So that is the nth degree Taylor polynomial, basically when you want to write out a finite number of terms. There's this other thing called the remainder, which is basically the terms that you decided not to write out, okay? So illustrate what that would be. You guys hear that in my background? Okay, so there's a thing called a remainder. So a function for this particular question would be the e of x, right? So there's a Taylor series representation, which is this thing right here. But you can sort of think of it as two parts. So if I write out, say, just the first three terms like we did over here with the second degree, x squared. Let me write it the other order. So 1 plus x squared over 2 factorial. This is not the whole Taylor series. So there are terms, oh yeah, my bad. Okay, so writing on the bottom here. So here's the first three terms, but this is not the whole Taylor series, right? Because there's obviously more terms that we didn't write. So let me just show the terms that I did not write. So I didn't write this one and this one, right? And then there's more terms that I'm deciding not to write. You can think of it as two parts. So this right here is the remainder. We can call it R2 of x, and then we can write the part that we did write. This would be T2 of x. So the function is equal to the nth degree polynomial plus the remainder, which, I don't know, seems like fine. I don't think we're ever going to use this though, but you'll need to know it for notation purposes. Okay, let me go back to the PowerPoint. So going back to this example we did where we found the Taylor series for 1 over x squared. So that is a question where like you actually have to derive the Taylor series on your own, which is very time consuming because you have to find the derivatives and then find what's the pattern for derivatives and then all that. I'm not going to ask you to do that on the exam. But in theory, you could do this for a lot of functions, right? So I can give you a different function, say f of x equals, say, like sine of x or whatever. And you can, go find the derivative and find the pattern. But it will be very time consuming. So what people usually do is there are some Taylor series in math that are extremely popular that people just have it on a table somewhere. So let me go back to where we were. Here we go. So this is a table that lists out some of the most popular used Taylor series in math. I don't know how many of these we did. I know we did the first one because that one was just part of the power series chapter. And then e to the x, we looked at that today. And then we have a lot more Taylor series. So there's one for sine of x, cosine of x, arctan, ln, and that one over there. So yeah, you can go ahead and use this table for every question going forward. If a particular question wants like a Taylor series from this table, you can just use it. Okay, you don't need to derive it yourself. All right. Now we can look at some examples that are more representative of what I will test you on. So let's look at this one. This is actually straight from your homework, actually. So yeah, this one says find the Taylor polynomial t sub 3 of x for the function f centered at the number a. What is number a? Oh, a is 4. Okay. So yeah, this is a good one. Really quickly, when we say t sub 3 of x, what's the degree there? It's kind of obvious. Yeah, so we're asking you to find the third degree Taylor polynomial, okay? I have the answer right there, okay? Let's see how we can get that. Let me copy the Taylor series formula. Okay, so there's the formula, and then this is the answer just for reference. Okay, so find the Taylor polynomial to the third power. So what we need to do first is just see what information we have. So the first thing we can plug in is the center, right? The center is 4, which means a is 4. So let's plug that in. So this will be n equals 0 to infinity of f to the n of 4 over n factorial or x minus 4 to the n. So that's what we have so far. Since we're only looking for the third degree polynomial, we don't actually have to write out all the derivatives. We just need to write out enough derivatives until we get to the term with x to the third. So let's see how many we need. If I write out the first function, that's just 1/4. If I write out the first, sorry, not 1/4, over x. If I write out the first derivative, what's the derivative of this function? How do I do this again? So it's x to -1. So you bring it to the front and then you subtract 1. Is that right? Is that the derivative? I think that's the derivative. Yes, okay. Because I almost said ln of x, which I like, that's definitely wrong. Okay, so that's the first derivative. Let's take the next derivative. So this is f double prime of x. So that would be positive 2x to the -3rd, right? And do we need another one? I think we do need another one because it's to the third power that we need. Equals -6x to the -4. Yeah, I think that's how much we need. Okay, and then we have to evaluate all these derivatives at the center. So evaluate it at a equals 4. So f of 4 is 1/4. And then f prime of 4 is that -1/16? That's right. Let me know if I make a mistake because I'm probably going to make a mistake soon. F double prime of 4 is, so it's 2/x to the third. 4 times 4 is 16 times 4 is 64. Okay, and then f to the third when you plug in 4, that's negative 6 over 64 times 4 is 122.56. Okay, so there's all your derivatives evaluated at a equals 4. I think that should give us enough information to write out the first, or enough terms in the power series until we get to the third power, right? So now let's write out the power series. So here's a Taylor series. So when n equals 1, when n equals 0, what term do we get? We're going to get f0 of 4 over 0 factorial x minus 4 to the 0 power. That is the first term of the Taylor series. Let me just give myself more space. The next term of the Taylor series is f to the first power 4, right? The next term is when n equals 1. That's 1 factorial x minus 4 to the first power. And then plus, the next term is f2 of 4 over 0 factorial x minus 4 to the second power. And then f3 of 4. Sorry, I made a mistake here. This is supposed to be 2 factorial. Now it's 3 factorial, and then x minus 4 to the third power. So at this point, we can stop because this term is to the third power, which is all we need, right? Because the question specified t sub 3 of x, which means to the third power. So we just need all these are all the terms we need. Now we just need to plug everything in. So f0 of 4, what was that? That was this number here. That was 1/4. So this is equal to 1/4. 0 factorial is just 1, and then x minus 4 to 0 power is also just 1. So this is just 1/4. And then the next term is f of 1 of 4, which was negative 1 over 16. So let me change this to a negative sign. So negative 1 over 16. 1 factorial is just 1, and then we have x minus 4 to the first power. All right, now moving on to the next term, we have f of 2 of 4, which was 2 over 64. So it's 2 over 64. 2 factorial is 4. So this is actually, I'm going to write it. I'm going to write it like this. 2 over 64 over 2 factorial, and then x minus 4 squared, and then minus 6 over 256 over 3 factorial. X minus 4 to the third power. Okay, so there's your Taylor polynomial. We should probably simplify this. So this is 1/4. This one's simplified. And then 2 over 64 divided by 2 factorial. I think the answer was over there, wasn't it? Yeah, it was 1 over 64. Okay. So this is 1 over 64, x minus 4 squared. And then this was, let me just look what they have, negative 1 over 256. X minus 4 third. Okay, so there's your answer. Here. So that would be your Taylor polynomial, okay? So just to sum up everything we did. So to find the Taylor polynomial, we have to write out the derivatives and then evaluate the derivatives. These derivatives will help us get the coefficients basically. So once we find these values, we plug these values into here, and then we write out the Taylor polynomial. Okay, yeah, so that's probably something that I will ask. Any questions on that? I mean, I know there's going to be like parts that you don't understand, but I guess it takes time for you to figure out what you want to ask. So you guys can keep thinking. I will move on to the next example for now. Okay, so what's supposed to be the general formula for 1 over x? Okay, yeah, I can answer that. So if the question wanted you to actually find the Taylor series for 1 over x, then you would have to find the general formula. But this question doesn't really want you to find the whole Taylor series. It just wants you to find the first few terms of the Taylor series only up until you get a degree of 3. So for example, if this question asks you to find, say, find the Taylor series, then what we need to do is we need to actually find out what's the pattern for the derivative. So what is f to the n of x? Okay. But we don't need to do that here because they're not asking for a whole Taylor series. They're just asking for the first, like here, 1, 2, 3, 4 terms. So that's why we don't need the general formula. Is that okay, Devin? All right. How do you know which derivative to stop at? For this question, the reason why we know we can stop at the third derivative is because if you look at the powers of our polynomial, it goes up by 1 each time. So for example, when n equals 0, that's going to give you a power of 0, right? Because your power is over here. And then when n equals 1, that's first power. And then when n equals 2, that's second power. When n equals 3, that's third power. So because they are asking for the Taylor polynomial of degree 3, that's why we can stop at the third derivative. So here's third derivative. We wouldn't need to go to the fourth derivative because the fourth derivative would correspond to the term of degree 4, which we don't need here. So that's how you know what derivative to stop at. Does this mean that every degree after the third one becomes the remainder? Yeah, basically, yeah. So for example, if this question asks you to write out what is r of 3 of x, then that would be like the next term after the one in our answer, and then the next term after that, yeah. Because remember, like T3 of x, that's not the whole Taylor series, it's just part of it. Yeah. So for every question asked at third degree, we stop at a third derivative. Actually, that's not necessarily the case. So there are some functions where the Taylor series actually, the degree does like, sometimes they skip degrees. So let me go to the table that I was showing you earlier. So this table right here. So notice how for some Taylor series, the degree goes up by 1, but for some Taylor series, it doesn't. So like for example, the first and second Taylor series in this table, you would need to go to the third derivative if we ask you for t sub 3 of x, because it goes up by 1. But notice what happens for, say, sine of x. So for sine of x, the first term has degree of 1, but the next term has degree of 3. So for sine of x, it wouldn't necessarily be the third derivative. Yeah, I want to say, so for every question asked for a third degree, stop at a third derivative. For the question that we just did, isn't the second derivative showing the third degree? Let me see. Let me go back to our work. So here's our work. Isn't the second derivative showing the third degree? You mean this thing right here? You mean that thing? I mean, the second derivative was a function to the third degree. But when I say third degree, I'm not referring to like what the second derivative was. I'm referring to the degree of the Taylor series. I'm referring to this degree over here, which is not the same as the degree of the derivative function. Yeah, because when in the Taylor series, when n equals 3, that's this term here, which requires the third derivative, which happened to be a function to the fourth degree, but like it didn't have to be. Yeah. Okay. Let's go to another example. All right, so this is another type of question that I'll ask you. So let's see how this one works. All right, so this one says, consider the function f of x equals x sine of x. All right, I am considering that function. Let me paste the Taylor series formula. There it is. Okay, so here we're saying approximate the function with a Taylor polynomial of degree n. What's n? 4. Okay, so they're asking for a Taylor polynomial of degree 4, right? So essentially what they're asking us is to find t sub 4 of x again. So we are trying to find this again. Okay. And then the question also wants us to use a center a equals 0. Okay, so this is a Maclaurin series, right? Because they're saying a equals 0. So center is 0. So this Taylor series is also a Maclaurin series. Okay. So there's actually two ways of doing this question. The first way is actually just to do it like how we did the last question, which is, to find a derivative. So f of x equals x sine of x. F prime of x, you can find the next derivative, and then you can find the next one. This is the second derivative. And then you can, keep going. But there is a reason why this method would actually not be very good. Does anyone see why we wouldn't want to find all these derivatives? Yeah, so finding the derivative of this function, finding the derivative once will probably be okay because that would just be product rule. But if you were to find the second and third derivative, that would get quite tedious, right? So that's why we wouldn't want to go this route. But if we really needed to, we could. It would just take us like 4 hours, right? So what's the alternative method? So the alternative method is actually to recognize that this function, x sine of x, there's a particular part of that function where we can actually use the table that I just gave you. So notice how this function includes sine of x, right? That is one of the functions that are included in the most popular Taylor series used in math. So let me just go back to that table. Where was it? Okay. So here. This is the one I'm paste. Okay, so this is pasted from the table. So here is the Taylor series for the sine of x function. Now you might be asking, well, how does this help us? Well, you can do the following. So instead of writing f of x is equal to x sine of x, I can also write it as x times the Taylor series of sine of x, which happens to be this. So this is n equals 0 to infinity of -1 to the nth power, x to the 2n plus 1 over 2n plus 1 factorial. Do you guys see what I just did? Okay, so this is actually good because now we actually have the Taylor series for our function, like the general Taylor series. I can bring the x to the inside of the summation, right? So this would be n equals 0, infinity, -1 to the n, x to the 2n plus, this is x to the first power, right? So if I bring it inside, it'll be 2n plus 2 now. Okay. So yeah. What was the question asking us to do? to find t sub 4 of x. So write out the Taylor polynomial until we get to the 4th degree. Okay, let's do that. So we already have the formula for the Taylor series, so let's just use that. The first term in the Taylor series is when n equals 0. So when n equals 0, let's see what we get. This is going to give us -1 to the 0 power, x to the 2 times 0 plus 2 over 2 times 0 plus 1 factorial. Okay, let's simplify this to see what this term actually is. So this is just 1 times x squared over 2 factorial. Okay, so this is the first term in the Taylor series. Let's do the next term, right? Because we're not at a degree of 4 yet. So the next term is when n equals 1. Right, so this was n equals 0. Now let's do n equals 1. So we're going to have -1 to the first power, x to the 2 times 1 plus 2, and then 2 times 1 plus 1 factorial. Let's see what this term gives us. So this would be -x to the 4th over, is that 3 factorial? Yeah, I think that's 3 factorial. Oh yeah, this is the 4th power, so we're done, right? Wouldn't it just be x squared? Which part? Two to the 0 plus 1. Oh yeah, you're right, yeah. This part. Well, okay, like that, right? Okay, I think we're done here because this is already to the 4th power. So we don't need to go any further. This is t sub 4 of x. All right, I think, do we have the answer for this one? Yeah, so x squared minus x sub 4 over 6, is that right? Yeah, that's right. I thought we were supposed to plug in 4 to n. N is the index of the summation. So it always starts at 0 and then you go up 1 at a time. It just so happened that in this particular Taylor series, when n is equal to 0, that gives you the x squared term. And then when n is 1, that gives you the x to the 4th term. Yeah, because remember, like we're not saying to stop at a particular index. We're saying to stop at a particular degree. So in this particular series, the index and the degree doesn't really match, which is why this one's a little bit weird. But the index of n equals 1 was already the 4th degree, so we stopped there. Right, so t sub 4, this is the 4th degree. Okay, so that's your answer. Let me just box that. This is your Taylor series for x sine of x up to degree 4. So what's the difference between this example and the previous example? So the previous example, we didn't have the general Taylor series for our function, right? So the best thing we could have done was just list out the derivatives and the coefficient and just plug it into the Taylor series formula, like this one right here. And that's fine and all, but for some questions, finding the derivatives over and over again can be quite time consuming. So for questions like this, they expect you to use one of the most popular Taylor series to like substitute it into the function and then proceed from there. Okay. So those two types of questions. Yeah, so that's all we have planned for today. So any last questions? If not, then I will have some announcements afterwards. Can we use a table or differentiate for certain terms, then plug them in? It depends. So the table has Taylor series for like those particular functions, right? So only if the question you're given actually has one of those functions as part of your function, then you can use a table. But for some of them, you'll have to just do it the normal way, which is what we did in the previous example. So let me go back to the table. So here's a table. So yeah, so you know, like if a question gives you, say, a function that has cosine of x as part of it, then you know you can use this table. What does R mean? Oh, R is the radius of convergence. Which is not really too important in this chapter. But yeah, I think you remember from Power Series that this was the first one was the one from the Power Series chapter. That one, remember how the common ratio has to be less than 1, right? So that gave you a radius of convergence of 1. So yeah, R is the radius of convergence. All right, any other questions? Okay, so what do I want to say? Right, that was the last topic. So this is one of those topics where you need to, do a little bit of self-study after the lecture, which is perfectly fine. Like I had to do the same thing when I was learning this. But you will have more practice because for the third exam, I will have a review sheet. Let's see, tomorrow's Wednesday. Reviews on Thursday. I'll definitely have the review sheet posted by the latest tomorrow evening. Okay, so by tomorrow evening, I'll have a review sheet posted, and then you guys will see what questions I expect. And then we'll go over the review sheet on Thursday, and then the exam is on next Tuesday. Yeah, so it's on, let me see what the date is. December 8th, which I think is the last day of class. So yeah, that's the schedule. Homework is optional, like I said. I did take a look at the homework for this section, and it's terrible. Like the question they ask you for the homework, they're like extremely hard. So I wouldn't actually recommend doing the homework. Well, actually, not all the questions are hard. Some of them are okay. Like the two that I pulled for today's lecture were from the homework. So those two I think were fair. But yeah, if you guys would like, I can look up some resources for you on questions where you do if you guys need extra practice with this particular topic, because I do feel like this is the hardest one. We only have to do quiz 8.1, 8.4, and homework 8. Yeah, so if you go on Lumen, let me show you Lumen right now. So there's two chapter 8 tabs. You only need to do up to the first chapter 8. So anything that's in chapter 8 continued is all optional. Okay. So if we manage to do homework, does that mean we're prepared for the test? I guess, yeah. A better representation would be if you're able to do the questions on the review sheet on Thursday. If we are satisfied with our 3 exam grade, is the final exam optional or mandatory? So the final exam actually counts as 2 exams when it's being averaged. So even if you're happy with your 3 exam grades, you still want to take the final because it's 2 exams. So if you decide to skip the final, you're gonna have a 0 average in regardless. So you should probably take the final. 3rd exam is November 8th. Because if your final is the lowest grade, then it counts as 1 exam instead of 2 exams. It counts as 2. Okay, so yeah, that's all we have for today. How is our final structure? Is it 1 question per topic? I don't know. I haven't decided that yet. Yeah, I haven't thought much about the final, but all I know is that all the questions are going to be pulled from the 3 exams that we had. I haven't decided how many questions though. Same question form, different numbers. I mean, it's not just going to be different numbers. Like here's the thing. So if I just make it different numbers, like that's really not doing much. So the way I explain it is like, for example, if I pull out, say, I don't know, what's a topic that we did? Like the one where you had to do geometric series or something, right? So if I decide to pull that question out, it's still going to be geometric series, but it'll be a different geometric series. You know what I mean? The whole day. Are you talking about the final, whether it's class time or the whole day? I think it was. I don't know. I feel like they released the schedule for the final to everyone, but I think it's 5:20 to 7:20. So it's not class time. Well, it's close to class time, but it's not the whole day. So I think it's 2 hours from 5:20 to 7:20, which is a little bit off of our class time, but that's when the final is. Oh yeah. So yeah, that's all we have for today, guys. So um, I'll have the review sheet up soon, and that's all for today. So I'll see you guys Thursday. Final is 16th. 16th? No, I think it was 15th. Final should be 15th. Should be on a Tuesday as well. Will you post a review sheet for the final? So there's no review sheet for the final. The reason is because the review sheet will have questions from your exam. So your 3 exams will count as your review sheets.